This is problem 91 of Neetcode 150 redundant connections. So we are given a connected unidirected graph with n nodes, and they're going to be level from 1 to n. And we know for sure that we have a cycle. So they're telling us that initially there's no cycle, and then we add a cycle, okay? And they're saying that there's an edge that has two verticals, okay? They're also telling us that we're going to be given edge, which is a list, which is going to contain a list of basically all the nodes that are connected to one another. So let's take an example like here. We can see we have a perfect square, right? So what do we have to do now that we know that we're going to be given nodes, are going to be given edges? What do we have to do? Well, we're going to have to return an edge that can be removed so that the graph basically becomes a tree, right? So if we take a look at the example 1, we can see that right now we don't have a tree because there's an edge that creates a cycle. So there's definitely one of them that will have to be removed. And if, frankly speaking, by just looking at it, we can remove all of them. So we could have a tree that the parent node is 3 and whose children's are 1 and 4. But they're telling us that in the case where there are multiple answers, we're going to have to return the edge that appears last in the edges input. So for example, here, if we can see the edges here, we're going to realize that the edge 2 and 4 is the last one, right? So if you revert the edges and you take the first index, you're going to get 2 and 4. So we're going to have to remove 2 and 4 so that the parent nodes is 3 and its children are 1 and 4. So there's a pretty clever trick that we're going to use to solve this problem. We are going to use depth first search. So if we take a look at this example here, we can see that we could potentially have a tree if we remove a link, but now we have a cycle. So what I will do is that I will call the depth first search function on every single node, and I will go see its children's. So it's going to look like this. I will start at 1 and I will go see 3, and I will go see 2. A couple of things we have to do. First, to know it's well, at this point they're not children's. They're like 3 and 2 can be seen as the neighbors, so the direct nodes that are connected to 1. So we're first gonna have to create a hash map, and in this hash map we're gonna store the neighbors of every single nodes. We're gonna have to keep track of the nodes that we visited for sure. And we're going to also have to, in our depth first search function, pass the parent, because otherwise, from 1 when we call its first neighbor 3, well, at 3, if we don't keep track of its parents and just call 1 again, well, we're going to call 1, and 1 is also going to call 3 back. So we're going to have an infinite loop. So we have to make sure that we're going to pass the parent. All right. You can see a couple nodes here are involved in the cycle. We have the nodes 1, we have the nodes 3, we have the nodes 2, we have the nodes 4. The nodes 5 is technically not in the cycle if we consider the cycle to be this closed loop here. Okay, 5 is excluded. All right, so we're gonna have to find a way to basically have a set that contain all the nodes that are inside the cycle. And what I will do after this is that I will simply revert this, right? So this is edges that you can see top left. So if you revert this and you take the very first list that appears, you're gonna have 4 and 5. So you can check basically if 4 and 5 are inside the list of the cycles. It is not, so we're gonna keep going. And you're gonna go see that 2 and 4 are in the list of cycles. So you're gonna return 2 and 4. So this is how we are gonna find the two all the edges that can be removed. So um, we might gonna fairly ask how we can keep track of all the values or all the nodes that are inside a cycle. What I will do is that I will create a cycle start that has the value -1. So I will just keep this. Let's say we call this C here. So C is going to be equal to -1. And as long as the value, so as long as the neighbors we're visiting have not been seen yet, we're just going to keep going. So at 3, we're going to go C4. And at 2, well, we're going to go C4 again. Um, well, at 4, we'll notice that we already saw this value. So this is the really moment where we're visiting either from, no matter what, it doesn't matter which side you're gonna start from, but you're gonna realize that 4 has already been seen. So we're gonna set the C to the value of 4. And now we're gonna just return this function. So we're gonna go backtrack here like that. And as long as the value 4 has not been seen again in the backtrack, we're gonna keep going. So we're gonna go C1. At 1, we're gonna go back to 3. 3, we're gonna go back to 4. And this way we're gonna go back to 4. And every time that we call the neighbor of 4, and we see that this neighbor's value is not equal to the C that we created up here, we're just gonna add this value inside the cycle set. And the thing that is important is that this is going to be done in backtracking, meaning that the call 5 here is not going to be included because we don't want to include 5 inside our list of scene or list of cycles. So we are just going to call this on our backtracking way. All right. So let's start coding this. First, we need to, well, I'll create the n variable, which is going to hold the length of the edges. Now I'll create my hash map. And I will actually make use of the fact that the nodes are labeled from 1 to n. So I will create my simile hash map, and I will create a list basically for from 1 to n. So this is going to be done by saying in the range of r plus n plus 1, so that the index 0 is not going to be used inside this neighbor list of lists, but it is not a problem. And now we're going to have to actually put the neighbors of a particular node. So this is going to create basically if n is 9, we are going to have 10 empty lists, and the first list is not going to be used because it has index 0. But the other list with the index 1, 2, 3, 4, 5, 6, 7, 8 will be used, and we're going to use that. We're going to use the value of the nodes to be the index inside this list. So we're going to say for A and B in the edges. So we know that A and B are connected. So we're just retrieving like whatever the two value are. So initially we're going to have 1 and 2. So we're going to have, for the first call, it's going to be for 1 and 2 in edges. All right, so what do we want to do? Well, in the neighbor at the index 1, append 2. And in the neighbor at the index 2, append append A. So by doing so, we're going to have basically a sort of hash map with all the neighbors of every single nodes. Great. So now we're going to have a scene set. What I'm going to do is that I'm going to create a value false for all the nodes. So I will say for n+1 again, because we want to make use of the indexes of this scene. So we're gonna have, if n is 9, we're gonna have basically 10 falses that are gonna be indexed from 0, 1, 2, 3, 4, 5 up to 9. So we can now use basically the value of the edges as the indexes to navigate this scene list. We're gonna have a cycle, and this cycle is gonna be a set. And finally, I need to create my cycle start, which is basically the value that will hold the first value that has already been seen. So initially it's going to be -1 because I know that the edges are from 1 to n. Could be 0 as well. Could be -infinity. Could be -10,000. As long as it is not a positive integer, because we know that it might gonna show up in the edges. So I will create a cycle start, and I will set it equal to -1. Now I will create my depth first search function. So as we spoke about earlier, inside my depth first search function, I need to pass the node, and I also need to pass the parent to avoid doing some sort of ping pong between two nodes again and again in an infinite loop. Notice that cycle start has to stay the same through all the recursive calls. Right now, I just created cycle start up here without specifying self.cycleStart. This is a bit risky because it's going to be changed every single call. It's not going to stay the same value every time we make a call. So to do so, we are just going to, we either create self.start, and we always have to then say self.cycleStart every time we refer to that variable. Or the second option we have is that we just say non-local cycle start, and this is going to do the exact same thing. All right. So now the first thing we want to check inside of the first search function is basically we want to check if we've already seen this value before. So we're going to say if seen at the node we're passing. So if this is true, we want to set that cycle start equal to that node. All right, and then we return true. Great. So after this, if we actually keep going inside our call, it means that we haven't seen that node yet. So we're gonna actually set it to seen by saying that this is now equal to true. Okay. And now we're gonna go see its neighbor. So I'll say for Nate in neighbor and the index node. Okay. So now we're going to go see all its neighbor, and we're going to go call a depth first search function on them as well. Notice that it is, we will, in pretty much all our call, send a depth first search call on the parent itself. So we want to avoid this because it's going to create an infinite loop. So what I will do is just say that if the neighbor is basically equal to the parent that we passed in our call, I want to continue. I don't want to keep going in this. All right. And after this, I will call my depth first search function, passing in the neighbor and the node as the parent. And if this returns me true, right, it means that within this call, um, there's a cycle. So one of the child or one of the neighbor actually was in scene when it was called. So we found a place where we have a cycle. So if this returns true, knowing meaning that we have a cycle, first, if the cycle is not equal to the initial value, so if cycle start is not equal to -1, it means that it is set to another value. So in our example, it was 4. So while this is 4, we are going to add to the cycle. We're going to add that specific node that we're at, because we know that this node is part of the cycle. All right. And right after this, we want to check if that particular node is equal to that cycle start, because at some point we're going to call back our value 4. And now I'm referring to the example we did on the whiteboard. When we go back to that value 4, we know that we actually went through all the values. So all the values in the cycle are now inside the set cycle. So what we can do is that we can just set back our cycle start equal to -1. All right. And we can return true. All right. So if we never return true in each of these call, well, it must mean that there's just no cycle at all. So we can return a false. So that is our depth first search function. Now we can call it, knowing that the first node we're gonna call is 1, because the nodes are gonna appear from 1 to n being the number of nodes we're being given. And I will set the parent to -1, just an insignificant number, so we can we know that it has no parent since it is the first node we're passing in. And now this is where we just want to reverse our hedges list. So I'll say for A and B inside reverse edges. So now if the two values A and B are actually in cycle, we're going to access basically the back or the end of the edges list. So this is like, remember, we want to return basically the last entries, right? So in our example here, where we add a perfect square with the nodes 1 to 4, we return 2 and 4 because this was the last entry. So by reversing it, we're initially going to first find 2 and 4 as the A and B. So what we're going to do is, so we're going to check if A and B are in cycle. So if A in cycle and B in cycle, so if they're both in cycle, we are going to return A and B, right? Otherwise, it must mean that the edges is not part of a cycle. So we can just keep looping for the second farthest value and send it if it ever happens to be in cycle. If we never return this, it must mean that this is not probable. There are no chances that we don't return anything, because the problem tells us that there will be a cycle for sure, but just to be safe, we're going to return an empty array in the case where it doesn't work. So let's try this out. So we have an error. Okay, so I forgot. Yeah, there was a dumb error. So basically, forgot my equal signs. Let's test this out again. It works. Awesome. Cool. So I hope you learned from this video, and I hope to see you in the next one.